Hey everyone, think about this for a second. Right now, in this exact moment, we are swimming in an absolute ocean of invisible energy. It's true. We are completely surrounded by a constant, dynamic flow of electromagnetic energy that our eyes just completely ignore. But what if we could harness it? What if understanding the fundamental rules of how that energy moves through space could actually give us the superpower to see straight through solid matter, to look inside the human body itself? Well, that is exactly what we are going to explore in this explainer.
Here's our roadmap for today. We're going to cover 1. Meet the photon, 2. The wave equation, 3. The electromagnetic spectrum, 4. Waves versus particles, and finally, 5. Energy and matter.
All right, starting off with section 1, meet the photon, the smallest bundle of energy.
Okay, let's dive right into this. We really have the ancient Greeks to thank for recognizing the totally unique nature of light. They didn't consider it just another basic earthly element. They gave it its own separate special status, calling an atom of light a photon. And honestly, that's a concept we still rely on heavily today. So what exactly is a photon in modern physics? Well, just as an atom is the smallest measurable piece of a physical element, a photon is the smallest quantity of any type of electromagnetic energy. You can picture it as this tiny, discrete bundle of energy, what we often call a quantum. But here's the absolute most crucial characteristic you have to remember. It is never, ever sitting still. A photon is essentially an energy disturbance constantly traveling through space, and it always travels at the exact same constant velocity in a vacuum. The speed of light. That is 3 times 10 to the 8th power meters per second. Fast, right? But how does this little bundle of energy actually move through space? It moves in what we call a sine wave. To kind of ground this abstract idea in physical reality, just think about some everyday analogies. If you strike a tuning fork, you know how its prongs vibrate sinusoidally back and forth? Or if you secure a rope to a wall and whip your arm up and down, you can physically see a wave traveling down the length of it. This sine wave model perfectly describes how the electric and magnetic fields inside a photon vary as it races forward at the literal speed limit of the universe. And visualizing these waves side by side brilliantly illustrates one of the primary measurements we use, amplitude. Imagine 3 distinct sine waves where the spacing between the peaks is identical. They're traveling at the exact same speed, but the only difference is how tall they are. Amplitude is defined mathematically as 1/2 the range from the highest point, the crest, to the lowest point, the valley. So waves can be identical in almost every single way, differing only in the sheer height of their amplitude. Moving on to section 2, the wave equation, the math behind the movement. Now that we can sort of visualize this traveling sine wave, we need a way to mathematically measure it, right? There are 3 primary parameters we use to describe this energy: velocity, frequency, and wavelength. Now, since we already established that the velocity of all electromagnetic energy is absolutely constant, it's always the speed of light, how do you think frequency, which is the number of wave cycles per second, and wavelength, which is the physical distance between those wave crests, relate to one another? The answer lies in the electromagnetic wave equation. In this equation, C stands for the constant velocity of light, F is for frequency, and the Greek letter lambda represents wavelength. Because that C variable can never, ever change for electromagnetic energy, it acts as a permanent anchor. Meaning if the frequency value on one side of the equation changes, the wavelength value on the other side has no choice but to adjust itself so everything stays perfectly balanced. And this brings us to a vital rule you absolutely must remember. For electromagnetic energy, frequency and wavelength are inversely proportional. Think of it like a cosmic seesaw. If the frequency of a wave goes up, the distance between the waves, the wavelength, must go down, and vice versa. As wavelength decreases, frequency has to increase. They are forever locked in this inverse mathematical dance. All right, section 3, the electromagnetic spectrum, exploring 25 orders of magnitude. We've spent a bit of time looking at the micro-behavior of a single photon, but photons actually exist across a vast continuum. We're talking about the massive electromagnetic spectrum. It spans over 25 orders of magnitude. And what is absolutely wild to realize is that whether you're tuning into standard broadcast radio waves, feeling the heat radiating off hot asphalt as infrared light, or measuring the ultra-high energy of a gamma ray, you are fundamentally looking at the exact same thing. They are all just bundles of energy traveling at the speed of light. Literally, the only difference is where they sit based on their specific frequency and wavelength.
Now, the whole spectrum is huge, but we can filter out a lot of the noise here. Because in medical imaging and radiologic science, we really only care about three critical regions. First, visible light, which is obviously crucial for actually viewing radiographic images, and we measure that by wavelength in nanometers. Second, radiofrequency, or RF. That's essential for MRI scans, and we measure it by frequency in hertz. And third, X-radiation, the absolute basis of radiography, which is measured by its energy level in electron volts. Historically, these were all discovered by different scientists at entirely different times, which is exactly why we use completely different units to measure them.
But hey, I want to throw in a quick, surprising fact before we keep going. Did you notice anything missing from those medical imaging windows? Diagnostic ultrasound. And there's a good reason for that. Ultrasound is fundamentally different. It is not a photon. Ultrasound is a mechanical wave of moving molecules. Because it requires actual physical matter, like human tissue, to travel through, it doesn't belong anywhere on the electromagnetic spectrum. Photons, remember, can happily travel through a complete vacuum. Ultrasound definitely cannot. Which leads us to Section 4, waves versus particles, the duality of electromagnetic energy.
So, if visible light and X-rays are fundamentally the same exact type of energy, why does light just bounce right off our skin while X-rays pass right through to reveal our bones? Well, it all comes down to their wavelength. This is explained by a fascinating concept called wave-particle duality. Basically, photons interact with matter differently depending on their wavelength. A really good rule of thumb is that energy interacts most easily with objects that are a similar size to its wavelength. Visible light has a relatively long wavelength, so it interacts with larger structures like living cells, specifically the rods and cones in our eyes. It behaves much more like a wave, kind of like ripples in a pond. X-rays, however, have incredibly short wavelengths. Therefore, they interact with the universe at the subatomic level, with individual electrons and atoms. Because of this tiny scale, an X-ray behaves much more like a physical particle, acting as a localized projectile. And let's tie this to a fundamental concept of quantum theory. The energy of a photon is directly proportional to its frequency, meaning the higher the frequency of the sine wave, the more energy the photon packs. Since we know X-rays have massive frequencies and tiny, tiny wavelengths compared to visible light, it completely makes sense that they carry significantly more raw energy. That's exactly what allows them to penetrate solid matter in ways visible light simply can't.
Finally, Section 5, energy and matter, the ultimate relationship in physics.
To wrap up today, we really need to look at how energy and physical matter actually interact at the most fundamental level. And you can't talk about that without bringing up Albert Einstein. His famous mass-energy equivalence equation, E equals mc squared, radically changed our entire understanding of the universe. It tells us that energy and mass aren't just related, they are quite literally two different forms of the exact same medium. You can actually convert one into the other, and they are inextricably linked by the constant speed of light squared.
So the mind-blowing point here is that we can actually use this math to calculate the physical mass equivalence of an invisible photon. Let's take a standard 1000 megahertz microwave photon. Using Einstein and Max Planck's equations, we find its mass equivalence is 7.36 times 10 to the negative 42nd power kilograms. That is a decimal point followed by 41 zeros before you even hit a number. It is infinitesimally small, sure, but it mathematically exists. It proves that energy and matter are deeply, irrevocably linked. Which brings us right back to our starting point. We live in an ocean of this invisible energy. By understanding exactly how a photon travels as a wave, how its frequency directly dictates its energy, and how it can literally behave like a particle to interact with the atoms inside physical matter, we can build incredible machines that capture those specific interactions. These basic principles of physics are the absolute bedrock of all modern medical imaging. So the next time you see an X-ray or an MRI scan, I want you to ask yourself, how are we manipulating these ancient invisible laws of the universe to literally save lives today? Pretty amazing stuff. Thanks for joining me on this explainer, and keep exploring.